we're looking at lesson 3 here, where we're going to start putting together these laws pretty clearly, and we're going to be practicing a lot of problems with them. So today we're just going to take it step by step with each law individually, and then in the next lesson, lesson 4, we're going to be talking about how do you decide which law to use if you're not told. Okay, so focusing on each one individually now. We first have Boyle's law. So the first important thing you make sure you do is you write down the actual law. So Boyle's relates pressure and volume. So you've got P1, V1 equals P2, V2. That means first pressure times first volume is equal to second pressure times the second volume. So an example of this type of problem, at constant temperature, you've got a 201 milliliter sample of hydrogen gas. It's collected and the pressure is that. What volume will the gas occupy at standard atmospheric pressure? There's that phrase again. That means 1 atmosphere. Let me scroll back down. Try that again. Here we go. All right, so standard atmospheric pressure is a phrase that means 1 atmosphere. Okay. So looking at this, we know our first pressure, first volume, our second pressure. So this right here is going to be our first volume, V1. This right here is our first pressure, and this is our second pressure. We need our second volume. So what we're going to do is we're going to start plugging things in. So we've got P1, P2, V2. So we're solving for V2 here. We don't know that. So I'm going to take P1, V1 over P2. I just start plugging in. So P1 from our problem is 185 kPa. V1 is 201 milliliters. And then P2 is going to be 1 atmosphere, or another way to write this so we have the same units is 101.325, which is that number we talked about the other day as well. Okay, so I'm just going to use that so kPa matches. So 101.325 kilopascals. I'm going to go ahead and solve. So if I multiply 185 times 201 divided by 101.325, you're looking at about 367. That's milliliters because that's what this unit is. Okay? Hopefully not too terribly hard. So second law we're going to look at is Charles's law. Charles's law relates volume and temperature. So we've got V1, V2 equals V2, V1. Okay? So for this law, we're just going to be pretty straightforward plugging things in as well. We've got a volume here. So this is going to be our first volume. This is going to be our first temperature. It's the first one we come across. Pressure is held constant. That's telling us that we're using Charles's law. What will the volume of the gas be at this temperature? That's our T. Okay. So remember that even though these both match in degrees Celsius, we always have to use Kelvin when we do any gas law problems. So I'm just going to convert this real quick. So 20 plus 273 is 293. And then 10 plus 273 is 283. Okay. Trust me, if you don't convert them to Kelvin, you're going to get a different answer. So looking at this problem now, we've got V1 T2 equals V2 T1. I'm solving for the second volume. So V1 2 over V1. Just rearranging that equation there. I'm going to start plugging in. So volume 1 is 50 milliliters. Our second temperature is 283 Kelvin divided by our first temperature of 293 Kelvin. Multiply and divide. You're looking at 48.3. No. Again, hopefully pretty straightforward. If you don't believe me about the Kelvin thing, go ahead and try it in Celsius. You will get a different answer. All right, so Taylor-Sachs law. This one relates pressure and temperature. So we've got the first pressure times the second temperature, second pressure times the first temperature. And again, for all of these, I just have some real life examples that you can read when these would come in play here. We're focusing on the problems though right now. So we've got a sample of gas contained at this temperature. So that's our T1, which needs to be Kelvin. So 25 plus 273 is 298 Kelvin. This is our first pressure. What would the gas pressure in the container be at this temperature? That's T2. So we've got 273 plus 52 is 325 Kelvin. Now we're going to start plugging in. So P1, T2, T2, T1. We are solving for our second pressure. Rearranging that equation there. This. Now I plug in. So our first pressure is 3 atmospheres times our second temperature of 325 Kelvin divided by our first temperature of 298 Kelvin. You multiply and divide, you're looking at about 3.27 atm. Again, this unit is always going to match the other pressure unit, in case you're wondering where that comes from. All right, the next one, Avogadro's law. Avogadro's law relates volume and the amount amount in moles like we talked about a little bit earlier. So you've got V1 N2 equals V2 N1. All right, so looking at this, we've got this amount of liters is V1. V disappeared, there we go. And this is the number of moles, the first number of moles, so N1. This is increased to this number of moles is N2, and we need to solve for V2 then. So what you're going to do is just start plugging in. So V1 N2, V2 N1. So we need to solve for V2. So V1 N2 over N1, start plugging in. So V1 is 5 liters, N2 is 1.80 moles, and 1 is 0.965 moles. Multiply across the top, divide by the 0.965 on the bottom, you're looking at about 9.33 liters. Again, that unit matches the other volume unit, which is liters. All right, so hopefully these aren't too bad. You just need to use the right equation and plug in for what you need. All right, so the combined gas law is interesting because it combines 3 different variables. So it combines pressure, volume, and temperature. So you've got P1, V1, P2 is equal to P2, V1. Okay? So you're going to see pressure, volume, and temperature in these problems. So we're looking through this. This is our first temperature. It needs to be in Kelvin. So 46 plus 273 is 319 Kelvin. This is an atmosphere, so that's the first pressure. And we know that it contains this volume. That's our first volume. How many liters, meaning we're looking for V2, would occupy at this temperature? So 0 plus 273 is pretty easy. And this pressure. So you're still plugging in like normal. You just have a couple more variables involved here. So we need to solve for P2 here. P1, V1, T2, equal to P2, V2, T1. I'm solving for P2. P2 is equal to P1, V1, T2 over V2, T1. All right, so looking here, I've got the first pressure I'm plugging in. That is 0.880. Got my first volume I'm plugging in, 0.600. My second temperature, which is 273, divided by my second volume. I'm sorry, we're actually solving for V2. My fault. Just change the V and the P. So I'm solving my second pressure in here. I've got 0.205. Okay. And then I have my first temperature of 319. So multiply 0.880 times 0.60 times 273, divided by the 319 times 205. Multiply and divide, you should get 2.20 liters. So again, not too bad, just a couple more numbers in play here. And the last one here, the ideal gas law. So the ideal gas law is interesting because there's only one of each variable. So it's PV equals nRT. Okay, so pressure times volume is equal to the amount of moles, which is N. R is that constant we talked about before. It's actually the ideal gas law constant, and temperature. So what's interesting is R can have one of these, basically 4 values. What you need to do is figure out what units you have and pick the right one. Okay, so if we're looking at this problem here, we want the pressure in atmospheres. So that means I want to pick the unit with atmospheres in it. You see how that one has atmospheres, the other ones don't? So that means I want to use this one. If this were to say mmHg instead, I would pick this one because it has mmHg here. Or if this said torr, I'd pick this one because that one has torr. So looking at this problem, what pressure means I don't know pressure. Exerted by, this is our number of moles, so N. This is our volume. This is our temperature. Okay, so 8 plus 273 is 281 Kelvin. All right, so we're just plugging in. So PV equals nRT. So I'm solving for P here, so P equals nRT over V. Plug in N, which is 4.5. Our R value, the one we're choosing up here, is 4.0806. Our temperature of 281. Our volume of 198. Came from right here. So 4.5 times the 0.08206 times 281 divided by 198. You're going to get about 0.524 atmospheres. And that's it. We're going to be working on these plenty, so hopefully you're going to have plenty of practice, but hopefully that made sense in terms of an introduction to these gas laws.